So yeah, my name's Zach Tatlock, and today I want to tell you about a way that we can provide really strong formal security guarantees for web browsers using a technique we call formal Shim verification. And this is work I did with my co-author Don and our advisor Sorin. So as we all know, browsers have become critical infrastructure. They're ubiquitous. They're running on devices we carry with us everywhere in our pockets. They run on our work machines. They're even on our appliances now. And we trust this platform with all kinds of sensitive applications. We use it for personal banking. We use it for health records. We share potentially embarrassing data on social networking with it. But despite all this trust, browsers have unfortunately proven to be quite vulnerable. So each year in the Pwn2Own competition, as part of the CanSec West Security Conference, up-to-date patched browsers are exploited by security experts with just the single click of a link. Now, vendors in the research community are aware of this problem, and they've built a lot of defenses, but it often feels like defenses are always a step behind. Everything's reactive. Attackers are able to exploit implementation errors and what seems to be an endless cycle of attacker finds subtle bug, vendors patch, attacker finds subtle bug, vendors patch, etc., etc. Now, there is one technique which can guarantee the absence of these sorts of errors and hopefully break the cycle, and that's fully formal verification. So for people who aren't familiar with it, fully formal verification consists of writing your system in a language that eases reasoning. It's easy to formally reason about your code. And then you simultaneously develop a formal correctness proof that shows your code has no bugs. Now, when you do this, what you get is a fully formal, machine checkable proof. So you don't have to trust me that I sat down with pen and paper and reasoned out my code and that I say it's good. You can actually check the proof yourself with a very small, simple proof checker and see if I'm being honest. So what do we get for all this trouble? Well, one shining example of this methodology is the ComCert-C compiler. And it formally guarantees that assembly programs it produces behave exactly as dictated by the input C program they came from. And recently, John Rager's group at Utah did a study where they were trying to automatically find compiler bugs. So traditional compilers like GCC and LLVM didn't fare so well. They found hundreds of bugs in these compilers. Can you guess how many they found in ComCert? No, they did not find any bugs in the verified components of ComCert. Yeah, that's exactly right. Exactly right. So none of the formally verified components of ComCert have had any errors to date. And this is after years and years of testing. And furthermore, ComCert is not some toy compiler. It produces code that's quality on par with that of GCC L1. It features backends for ARM, PowerPC, and x86. And Airbus is actually internally evaluating it for use. They're publishing reports on how feasible it will be used in real avionics systems. But ComCert is just one piece of the puzzle. There's formal verification for infrastructure going on at all levels of the software stack. So I'm sure many of you are familiar with the work on Cell 4. It's a verified operating system microkernel. There's also work on fully formally verified database systems and web servers, etc. And these systems are really the closest things we can build to bug-free code. So this sounds great. You apply this methodology, you have no bugs. What's the catch? The catch is that to do this, the first thing you do is throw away all your code. You then have to rewrite everything from scratch in an unfamiliar language. You have to formalize the application domain and figure out what it even means for the program to be correct. Then you have to reason about your code and prove every single detail, every possible execution of that program never does anything wrong. And in practice, this just requires heroic effort. It's really difficult to fully formally verify a realistic system and avoid the temptation to cut corners to ease the verification burden. And so this is really the scaling problem with fully formal verification that Dickie George was talking about this morning when some student asked him about it at the end of the talk. So if this is so difficult, how the heck are we going to apply it to a browser? I mean, after all, browsers have these huge, complex components that span millions of lines of code. These components interact in all sorts of subtle ways that make it difficult to anticipate how a change or bug in one component will affect other components. They access all kinds of sensitive resources like the network, user input, disk, things we really want to protect. And perhaps worst of all, they're constantly evolving. So even if we were able to take a snapshot of a browser today and formally verify it, which would probably take decades, by the time we got done, the proof wouldn't matter because browsers would have changed so much. And Don and I would like to graduate eventually, so we're going to take a different tack. And really, we apply an insight which is going to allow us to make strong formal security guarantees about these kinds of systems without reasoning about the browser code. So the first thing we do is we isolate untrusted code. We put it in a sandbox and restrict its ability to access resources. The second step is to introduce a Shim, which guards resources. So Shim is a wrapper or a reference monitor. And then finally, we formally verify just the Shim. And this guarantees security properties for the entire system. We know resources are accessed correctly. And we call this technique formal Shim verification. It's one of the main insights of our paper. And now in particular, we're able to apply formal Shim verification to the context of web browsers to build a new formally verified web browser that we call QUARK. And in QUARK, we're able to guarantee several security properties, a few of which are tab isolation. We guarantee that no tabs ever able to affect how the browser treats another tab. We also show cookie integrity, so cookies are only accessed by tabs of the appropriate domain. And we show address bar correctness. The address bar the browser displays correctly reflects the address of the focus tab. And we're able to prove the actual code correct. And this distinguishes us from previous efforts to apply formal methods to browser security. Instead of reasoning about a model, a simplified model of the system, we actually prove the code that gets run correct. So what you run is what you prove in this methodology. And that means we're forced to handle all the nitty-gritty details in corner cases of a realistic system. So let that sink in for a second. Okay, so this is what the rest of the talk is going to be about. First, we're going to zoom back out, look at fully formal verification, see how that workflow takes place. We'll talk more about formal Shim verification, and then we'll see how we apply it to QUARK. So in fully formal verification, the first thing we do is rewrite our system in a language that eases a reasoning burden. And typically, this is a language that looks like ML or Haskell. The next thing we need to do is formally specify what it means for that code to be correct. So this involves stating logical properties that characterize correct behavior of the system. Now, once we have these two pieces, we load them up in a proof assistant. In our case, we use the theorem prover called QUARK from INRIA. And once we have these in the proof assistant, we interactively show that the code satisfies the specification. And this is where you really need to bring some expertise to bear. QUARK isn't a simple system. It implements the calculus of inductive constructions, which allows us to bring exploit the full power of dependent type theory to reason about these systems and prove them completely correct. But once we've gone through that effort, once we have proven this, we can actually extract and compile down to machine code a system that we can run. And this is great because we get really strong security guarantees about the actual system. But again, the downsides, they have to throw away everything, write it from scratch. And with a big system, the proof effort is proportional to the size of the system. So then we need to reason about this huge code base. It's non-trivial. Okay, so let's zoom back to formal Shim verification and see how fully formal verification fits into that workflow. So first I'm going to bring back the diagram we saw earlier. And in our case here, we're talking about applying this to a browser, but the technique is general. It could be used with any complex system. So I'm going to abstract it to nice clean boxes. And so the workflow for when we want to implement formal Shim verification is to first adapt the untrusted code to a sandbox. And that requires going in and finding all the places where that code tried to access some sensitive resource, and instead replacing it with a request to access that through the Shim. The next thing we need to do is design the Shim so that it accesses the resources and provides an interface that the untrusted code is able to be effective, to actually accomplish what the code is supposed to do. Once we've designed and implemented the Shim, we then apply the techniques from fully formal verification, but just to the Shim. And this is really one of the key insights. We're able to provide strong security guarantees for the entire system, but avoid reasoning about the complex untrusted code, and instead just prove a small, simple Shim correct. And again, the thing to emphasize here is that what you run is what you prove. This is not a model. You're actually reasoning about the actual code. All right, so now let's look at how formal Shim verification applies in the context of web browsers and see how we built up QUARK. So in QUARK, the resources we care about are things like the network, the disk, screen, keyboard, mouse, user inputs, these sorts of things. And for QUARK, the browser takes the Shim takes the form of a browser kernel, which is similar to a browser kernel like in Google Chrome, except that in our case, the browser kernel is implemented, specified, and formally verified all in the demanding context of a mechanical proof assistant, QUARK. Once we have the browser kernel, the next thing we do is figure out how to split apart untrusted code into browser components. Now in our architecture, those components all run as separate sandbox processes, and their capabilities are severely limited. In particular, all they're able to do is talk to the kernel over a pipe. They can't make arbitrary system calls, they can't open new sockets, they can't read and write the file system. They can talk to the kernel over a pipe. That's it. There are two kinds of components in the QUARK system right now. The first are the WebKit tabs, and these correspond to versions of WebKit that we modified to interpose on any access to sensitive resources and instead redirect it as a request through the browser kernel. And the second component type are cookie managers, which we wrote in Python. And each cookie manager maintains the cookies for a single domain. Whenever it needs to communicate with tabs, again, it is forced to communicate through the browser kernel. So in general, there can be multiple instances of these browser components. Okay, great. So this is a high-level view of the QUARK architecture. But the thing that really distinguishes QUARK is the browser, its browser kernel. So let's zoom in on that and take a closer look at how it works. So there are three parts of the kernel we really want to cover. The first is its implementation. The second is how we specify its correctness. And finally, how we prove that the code satisfies that spec. We'll start off by going over the details of the code. The QUARK's kernel is structured as a message processing loop. And it's implemented in code that's sort of similar to ML or Haskell. And in this case, the core processing is all done by a function called kstep. And the way kstep works is that it starts with the current kernel state. It processes a request from a browser component. It writes out responses. And then it returns the updated state. And it just gets continually called in sort of an infinite loop. So every time we're going to process a message, we call kstep. After it's done, we call kstep again and again and again. So if we sort of zoom in, we see that here, the kernel state is really just a tuple. I'm only showing a couple parts of it. Here we have the currently focused tab and the list of all the current tabs. And the first thing kstep does is a Unix style select over pipes to different browser components. Once it has a pipe that's ready to read, it looks at where the request is coming from, and it responds differently. If it's coming from a user, the next thing QUARK does is it reads a command from standard in. Then depending on what that command is, it responds appropriately. So if the user wanted to add a tab, for example, QUARK would create a new tab. It would send a message to the tab over the tab's pipe, telling it to render itself, which should cause the tab to send back a bitmap of its updated display. And that'll get processed in a subsequent call to kstep. And then finally, the kernel would return the updated state, which includes the new tab as focused, and also adds the new tab to the list of tabs. Now this shows a representative case from kstep, but of course there are other cases. The user might additionally want to switch tabs or enter data into a form, etc. And tabs like to do things like access cookies, update the display, ask the kernel to fetch web resources, and so on. So this is a high-level view of how we're able to specify the kernel code. There are a few more details. We do have imperative programming features, which we use standard techniques from purely functional programming to represent. In particular, make heavy use of monads in our code. But at the end of the day, you get to write code that looks and feels a little bit, sort of C-ish, which is nice. So now I have some idea what the code looks like. Let's move on to seeing how we're able to specify the correctness. Now, in QUARK, we actually reason about the properties of the kernel in terms of the system calls it can make. And we call the sequence of system calls the browser kernel makes on any particular run its trace. And this can be a really long, basically list of syscalls. But it's not an arbitrary list of syscalls. We actually know it has some structure. It corresponds to a run of the kernel. And so those traces correspond to a sequence of calls to kstep. So it has this sort of nice inductive structure that we can reason about. And we use that when we're specifying the correct behavior of the kernel, or when we're proving it correct. So we'll see more about it later. Now, to give you a feeling for what the spec looks like, let's take a brief overview of the theorem for address bar correctness. I'm going to show you just a slightly simplified example. The full details are in the paper, and you can also check out our code, and it's available online. So the theorem starts off by saying, for any trace, tab, and domain, where trace is any sequence of system calls, if that sequence of system calls corresponds to a trace that the QUARK kernel could generate, and tab is the focus tab in this trace, and domain is what's being displayed in QUARK's address bar at the moment, then domain is also the domain of the currently focused tab. And so we can actually specify several security properties in this style. A selection of them are shown here. These are some of the more important ones. So we're able to show tab non-interference. In particular, that means that no tab can ever affect the way the kernel interacts with another tab. We're also able to show cookie confidentiality and integrity, which means that cookies for our domain are only accessed by tabs of that same domain. And we're also able to prove address bar integrity and correctness. We already saw address bar correctness. Address bar integrity just means that if the address bar is updated, the user was somehow in the loop. So now we've seen a brief overview of the QUARK kernel code and the specification. Let's move on to seeing how we're actually able to show that the code satisfies the spec. Essentially, the proof proceeds by induction on the set of traces QUARK could possibly produce. So the base case is easy. If you haven't made any system calls, you haven't done anything, so you clearly haven't violated any security properties. And in the inductive case, we assume we have some trace, which up to this point is valid. And then our obligation is to show, if we take an additional step, that all the security properties still hold. And so to prove this, we essentially proceed by a case analysis on case step. We ask, in any execution of case step, what kind of system calls can it add to the trace? And we need to know if those additional system calls will continue to satisfy our security properties, given that all the system calls up to this point did. And so this is where we need to drop down into the interactive proof assistant and actually carry out the details of the proof, with the help of the tactic language, etc. But it is a difficult part of the workflow. But the key insight from all this is that we're able to provide strong formal security guarantees for a browser using state-of-the-art components without reasoning about the complex code corresponding to things like JavaScript interpreters and HTML renderers. Now, I've said that our browser is, realistic or modern or uses state-of-the-art components, but I guess I haven't really given you a lot of evidence to believe that. So we actually have a quick demo. It's a video. And my co-author Dom made it. It's a little bit short and I have a lot of points to make. So talking might get old fast. Prepare yourselves. Okay. Okay, so Don's going to run some interactive searches here in QUARK. And you'll see that the browser is really responsive. The interface runs smoothly. It's actually worth pausing here to note what's going on. Every single keystroke, every mouse event, every network request, cookie access, all these things are passing through the kernel we wrote because the tabs are sandboxed. And that means every action has to pass through a formally verified kernel, which we implemented in a theorem prover and proved every detail of correct. When we started this, it wasn't at all clear that it'd be possible to build this realistic of a browser and fully formally verify it. And the key here, again, was formal Shim verification. It allowed us to provide really strong formal guarantees within such a demanding interactive setting. Now, as you may have noticed, when Don logged into Gmail, he didn't put in his username or password. That's because he was already logged in, and cookies work correctly in QUARK. And you can also see here that each tab is running a full version of WebKit. There's HTML rendering, JPEG decoding, there's a JavaScript engine. It's fully featured. And it might seem a little bit modest, but the blinking cursors actually took a lot of work to get working here. We adapted an optimization from Google Chrome called rectangle-based rendering. And what it does is it only redraws the part of the screen that gets updated. Here, Don's doing some interactive searches on maps for our favorite burrito shop, Don Carlos. It's really great if you're in San Diego. Highly recommended. And get a load, when you're zooming in, this moves really, really quickly. That takes advantage of another optimization that we did, adapted from Chrome, where we use shared memory to pass bitmaps directly from the tab into the kernel. We also support, I think you saw, other sites like Amazon and Facebook, which run really well in QUARK. In fact, we tested on all the Alexa top 10, but we don't really have time now to go into all the details. There's another video with a longer demo on our website. So one thing to notice here is that the address bar is a little bit non-standard. Right now, QUARK uses a text-based address bar because it was easier to reason about formally in the context of a mechanical proof assistant. But the point of this video is really just to convince you that QUARK is usable. It runs on demanding popular websites, and it works. So we can also evaluate QUARK in terms of its trusted computing base. In particular, the trusted computing base corresponds to elements of our system that we assume to be correct. So a bug in any of these components could completely invalidate our formal security guarantees. And there's two types of elements in the trusted computing base. The first are fundamental. They will always be in the TCB. There's nothing we can do about it. And that includes the statement of our security properties. So we assume that when we say something like tab isolation, and we state it formally, we've correctly captured our intuition. It also includes the logic, in our case, QUARK. So we assume soundness for the calculus of inductive constructions. And we further assume that the small, simple proof checker to check proof terms in that logic is correct. The rest of our TCB, which includes larger components, correspond to things that could eventually be formally verified and further pulled out of the TCB. That includes things like the OCaml compiler and runtime. There's currently a research project by some of the ComStr people called VeryML to make a verified implementation of OCaml. The tab sandbox, there's a project at Harvard called Roxalt on doing verified sandboxing, and the underlying operating system. And I think many people are familiar with Cell 4, which is done at the University of South Wales, I believe. And there's, so other components also can be verified. New South Wales, I'm sorry, yeah. There's UNSW, like, what's the N? New Zealand, not the UK. Thank you, yeah. University of New South Wales, thank you very much. Okay, so we've built this. These are things we trust. What do we get for this? Well, we've been able to formally prove some important security properties. And what that means is that if there are no bugs in our trusted computing base, then there is no attack that will ever violate our security properties. Now, of course, there are other security properties that we haven't formally verified. And there are attacks against those that may well succeed in QUARK. However, it's important to notice that QUARK isn't doing any harm. All the existing defenses that WebKit would normally run remain in full effect. We just haven't formally verified them, so there could be bugs. And there's also, other desirable security properties we'd like to show. For example, we haven't yet proven the same origin policy. In order to do that, we would need to refine our principles from tabs down to frames. But that task is greatly eased by the fact that we've already built up a framework that allows us to formally reason about security guarantees in the demanding context of a mechanical proof assistant. When we started off, again, it wasn't clear this would at all be doable. But now we have this foundation, there's a lot of future work that'd be exciting to explore. So a few of those things would include improving compatibility by implementing things like file system access, support for sound or browser history. And we believe these things can be added to QUARK without a major redesign of our architecture. Perhaps more interestingly, if we were able to add finer-grained notions of resource access, we could better support things like mashups and plugins like Flash. So we need to both have a better idea of who's requesting access to the resource, lowering down to frames or even finer granularity, and also what kind of resource they want. Instead of saying, you wrote something somewhere on the screen, be able to say you wrote to this region of the screen. And finally, it would also be nice to be able to formally verify some liveness properties. For example, formally proving that the kernel never gets blocked on any request from a browser component. So in conclusion, we had the main insight of applying formal Shim verification, which allows us to make strong formal security guarantees for complex systems while only reasoning about a very small amount of simple code. And we applied that technique in the context of web browsers by building a new formally verified web browser called QUARK. And we were able to show several important security properties for that. You can see more demonstration and get the code at this URL. And thank you very much for your attention.
Questions, and I'd like to remind you to please state your name and affiliation.
Perry Metzger, University of Pennsylvania. So a couple of questions. First of all, how large is the development of the code itself in QUARK, and how large is the proof development?
So the browser kernel, I believe, is around 750 lines, and the proof is around 5,000 lines right now.
Okay. Second of all, so Cook is strongly normalizing, as a result of which you can't actually build an infinite loop in it, whereas your shim is clearly running the state transform program in an infinite loop. So did you put a wrapper OCaml function that calls the extracted function, or?
Yeah, so actually, that would work. We do something a little more principled. So I don't know if you're familiar with the Why Not project out of Harvard.
Not fully.
So essentially, they represent the IO monad from Haskell, which allow us to formally reason about imperative programming constructs, in particular, non-terminating code.
Okay.
So they allow us to formally reason about those kinds of computations within QUARK.
And then they extract to an ML
Exactly
in a
right.
reasonable way. Okay.
Yeah.
And lastly, so how much of the how much of the peripheral stuff, like, I mean, you're clearly, I mean, Cook cannot directly represent the operating system calls and on all those sorts of things. You're modeling those on some level. Do you have any extra? I mean, how much extra code do you have in OCaml that to make the whole thing live?
I see what you're saying. So we have these sort of primitives, like read system calls.
You need those. Yes.
Yeah, so the primitives, I think the numbers are in the paper. I don't remember that number off the top of my head. But most of the primitive implementations are very straightforward. They correspond essentially to having OCaml make the corresponding system call on your behalf.
Okay.
But yeah, those details are in the paper. That's an excellent question.
So they're minimal.
Yeah.
Hi, Charlie Rice from Google. I'm wondering if you can expand a little bit more on what sort of challenges you had in specifying the security properties of something as complex as a browser and what you actually expect to happen.
So that's a great question. So initially, it wasn't even clear how to write it down. We actually spent a couple of months figuring out what to even say. And so the main insight came when we sort of adapted some notions from work in compiler verification, operational semantics, where we had this notion of a browser step. And so essentially, once we constructed the browser as this message processing loop, we had a very clear place we could put a loop invariant, and that allowed us to specify, in between every message exchange, what should be true. It gave sort of a cut point. And once we were there, we looked at other research, what previous techniques that weren't using full formal verification, maybe using model checking, so what kinds of things they wanted to establish. And then we looked at how we could sort of translate that into the setting of this sort of k-step inductive invariant. But yeah, it was a major challenge to figure out how to state those things. There are additional security properties stated in the paper. It might be good to look at those. But yeah, it took a lot of work, but that was sort of how we attacked it.
Sure. Thank you.
Kevin Borders, NSA. So I guess I had a follow-up question about the security properties. So what was your process for deciding which ones to go after? You mentioned same origin policy. Are there other ones that you think will be possible to prove or that are next on the list?
Yeah, so properties like the same origin policy are attractive, and we think if we modify our design slightly, change what the principles are in our system, they are tractable. There are other problems, security properties, that will be very difficult to do. So one property of formal shim verification is that you treat the bulk of the code as a black box. So any security property that depends in a fine-grained way on how that computation is done will not be amenable to formal shim verification. So in particular, if we wanted to restrict the way in which the HTML renderer worked, that would be really difficult because you have to start reasoning about those big, complicated pieces of code. So really, the key for formal shim verification is identifying these nice interfaces. So any security property that requires to reason across a clean, simple interface would be really difficult to do. I don't have an example of that off the top of my head, but that's sort of a way to decide how difficult something will be.
Thanks.
All right, we have time for one more quick question.
Is it quick? Yes, of course. Can you estimate the difficulty? The system requires you to, at some point, verify the sandboxing element of it as well, which you put as extra work. Could you somehow estimate the effort that would be required to verify the mechanism that you use to sandbox the untrusted code base?
So I think that the most relevant work to look at for that is the rock salt project. That's recently it's an active research project. One thing I would say is the people at Google have been working really hard and they built a really good sandbox. They put a lot of effort into it, and recently it was actually
but verifying it, how much? So in your case, 700 lines required 5,000 lines of proof code. I imagine
what's the verification overhead for a sandbox? That's a good question. A lot of times people estimate between like 10 and 50 lines difference. But yeah, check out rock salt. I think that will help answer that question.
All right, let's thank our speaker once again.